So what is it that we're going to do today? I'm just kind of wrapping up my assignment. So it's the third assignment for PH59 computational physics, and this is about the first two projects in this. So this is actually like a compilation of 3 to 4 projects. I'll just show you the thing. Right. So you just have mini project 1, which is just simulating an orbit. Mini project 2, which is to find the precision of Mercury. Yeah, and then the third one I think is the radial velocity method and synthetic exoplanet. So I've basically done the first two, and those are the core requirements. But since I have a bit of time, and well, I'm greedy for grades, as you all know. But yeah, so that's the point. I have some time, so I guess I can do this third one as well. He did say he'll give me bonus marks, so I guess it's worth it. So I have to read this exoplanet stuff. So they want to generate data for an exoplanet. I don't know what's going on. The first thing that they want to do is kind of very simple. Just have the center of mass rotating frame, and then they define the small r as just the relative position, and then they just figure out, okay, how is the relative position changing. So if I can get that, then since the center of mass is kind of constant, it's a closed system, so you know what will be the actual positions of the bodies, right? So it's just a very simple two-body system, and we have done all of this before. We have done all of this orbits stuff, like, so J, it has a lot of this stuff going on. So it's not that this is something new, it's just that now we are doing it numerically, so with computation. Okay, so we'll just have to read through this to understand what notation they are using. Yeah, and then that should be good. So they have, I guess, some F, so it's like 6 parts, shouldn't be too bad. So we'll do this. I also want to put some notes onto the notebook which I have. So I'll just show the notebook. And I kind of don't like running the notebook because it like takes tremendous amount of time. Okay, this is something that happens a lot in VS Code apparently. Yeah, I don't know what's with VS Code nowadays. Maybe I should move to a better ID. Anyway, so this is the notebook that I was referring to. Yeah, VS Code. It has some issues, like VS Code is not all that good for Python notebooks apparently, or any kind of Jupyter notebook. Okay, I'm just gonna close all this because it takes then lesser time, right? So that's the thing, like code folding allows it to kind of utilize less resources, and it will be better that way. So we just have like this very longest code that I've written for practically everything. So the code isn't the point, the code is the mundane thing. I'm just going to go over what I've done. So the first main project is about the closed and open orbits in modified gravity. When they say modified gravity, it's about, so they change the power law from inverse square to some other power with a slight deviation delta from the value of 2, or in this case 3 if you are going to think of it as r vector upon r cubed rather than r hat upon r cubed. It's just gravitation, normal gravity, alright, except you are slightly modifying it. So then the point, so they're modifying it with this delta factor. So for delta equal to 0, it is gravity. And you see that the angle that the planet makes with x-axis, it changes periodically. So it's just like going up, and then it goes down because after 2 pi it rolls back to 0. And yeah, the same thing with r. R hits a minimum at some point. This point is called the perihelion, and then when it's the maximum, it's the ephelion. Ephelion, I don't know how to pronounce that. And it goes like this cyclically, and it turns out that only the inverse square law and the Hooke's law, those are the only two kind of forces which can produce these closed orbits, and we'll come to what closed orbits are. So that's where this nr and n theta thing comes. So nr is the number of revolutions in just the distance basically. So like, so you see r is sort of sinusoidal, right? So the number of how do I call it? the number of wavelengths, if that's the way to define it. I mean, it's not a sinusoid, it isn't necessarily a sinusoid, it isn't, in fact, it just isn't. You'll see what it is, and It's not a sinusoid, but or is it? Wait a second. I think it is, right? I don't know. It's something, but the point is that it's periodic. So how many periods has passed? That's what NR is. Similarly, n theta is the amount of periods in theta which have passed. So like how many revolutions has been done. So starting from this, there's no revolutions being done, and then at this point, it's one revolution done. Now this thing is actually 1 year. So this point is the mark of a 1 year, and everything's in terms of years and astronomical units. Astronomical units is like kind of like the radius of Earth from the Sun, in a way. It's a semi-major axis, but okay, whatever. Yeah. So then, what was I going to say? So a closed orbit has this nr by n theta thing equal to some constant. So the idea is that at every revolution, your nr can only be incremented by some integer value. If that doesn't happen, something weird is going on. Yeah. And when I say revolution, I mean like revolution of the whole thing, not just theta, but like after a full period, which will be an integral multiple of both nr and n theta, you will have like a rational value of nr upon n theta. So if it isn't rational, then something whack is happening, and then we say that the orbit isn't closed because it's not periodic. So you can see that for this thing, theta is closed. Sorry, this orbit is closed because nr by n theta is consistently 1. It's not changing at all, so pretty obvious. Yeah, and we already know the period is 1 year and everything. So this is just a trajectory of the planet Earth, basically. Then part 3 and 4 is about that. What is a closed orbit? How do we define it? Why is it that a rational nr by n theta gives a closed orbit? All the mundane stuff which I don't really care about. You also have this thing theta r minimum, which is the angular position of the perihelion. Perihelion is where r is the minimum. And you also have this phi thing, which I'll come to that. But this thing is basically like going to give you the precession. So you'll see that for delta equal to 0, there's no precession. This thing doesn't change with revolutions. But for some other cases, which by the way are not periodic, but every revolution in terms of theta, your theta r minimum actually changes. So now the minimum distance isn't achieved at theta equal to 0, it's at some slightly different value, and it keeps on going. So for delta equal to 0.1, which is like a very large deviation from the inverse square law, you'll see that it goes all the way to 2 pi, which is messed up, but it is what it is. Oh yeah, theta equal to pi is the perihelion, because we have theta equal to 0 as the epihelion. Pretty normal. And once again, nr by theta is kind of constant. Even though you have these deviations, we don't really see the thing, because it is just the way it is. Anyway. Yeah, I think this is about closed orbits. Shouldn't this kind of be changing? I don't know. So defining perihelion, blah 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 blah. Yeah. Changes with revolutions, the effect is not visible in the plot for trajectory because the trajectory isn't all that elliptic. Same effect is also seen at the phi angle. I will come to that. So this is just about the precession. There's nothing complicated going on over there. Alright. Yeah, so now you can see that the nr by n theta thing changes. So up to a certain point it's 1, but then suddenly this changes, like this becomes very weird, and the reason that is happening is because your what do I call it? What is it called? Oh yeah, so the number of revolutions suddenly change because the theta is like going backwards, right? So anyway, the point is that r minimum is changing. So yeah. You see the same thing here as well. So the case with delta equal to 0, no deviations. Others have very small but persistent deviations from the initial ratio of 1. A closed orbit, now I go over the definition, why it is the way it is and all that. Then a Hooke's law like force. So then I do it for delta equal to minus 3, which is basically Hooke's law. And you will see that once again it's closed, as in it's staying constant, more or less. Then the delta equal to minus 3 case has its fundamental period for theta t match exactly with the delta equal to 0 case. But then for the radius, it's half of that of delta equal to 0 case, because it's going like back and forth, it's not going in a circle, it's different. Then we do it for some different initial positions and velocity, which is basically for Mercury at its aphelion, and you see a kind of different thing going on. And you also see this theta r minimum is like going down. Now you might think it's precession, but no, it's not precession. In a proper inverse square law, you shouldn't have anything like that, right? Even for something like delta equal to minus 3, so the Hooke's law, you shouldn't have any kind of precession. The reason this is happening is because Mercury's orbit is completely whack. It's very hard to integrate over, because near the aphelion you have very fast velocities, and away from it you have very low velocities, right? It's very elliptic, and you can see that over here it's highly elliptic, and it's constantly changing because of these problems, because the numerical method isn't good enough for this. So to change it, all we have to do is just take smaller time steps near the aphelion, which is what this time transform leapfrog thing does. And I won't get into specifics, but now it gives you no weird precision that we were getting before. Now it's just like going straight. Yeah, and once again you see that this is more or less a closed orbit, and this is just the same image but with this new integrator. Okay, so that was project 1. One thing I want to add to that is to see whether I can do the same time transformation but without using the method that they were using. So I'll just create a new method, right? That's the one thing. So all of this is over here. So I'm defining leapfrog, time transform, all that. So I'm just going to do so this is going to be not leapfrog time transform, so it's leapfrog adaptive step. Adaptive step, I think, yeah, that's a good name. So we don't need a W because we don't doing it that way now. Do we need a Q? Yeah, we do. The T thing, we do need the T thing, right? P A D T. So that's the thing. Over here, the dt is actually ds. So that's different, but it's fine. If here as well, it shouldn't actually be dt. So I'm just gonna write a comment over there. dt is actually ds, or more like delta s. I'm just gonna write it the correct way. Not that I'm just gonna be able to like read what's going on. I don't know, maybe he's just so accustomed to writing LaTeX that he will be able to understand it better than just writing ts. Or maybe I'll just write it as ts, you know, like a plain old programmer. Okay, anyway, so I leapfrog time adaptive time step thing. So now let's see keyword arguments. The I think we do need T, we need the Q, which is the position, P, which is the momentum, the acceleration, we need that, we need all of that. All right, so now what do you have? You have Q mid is Qi plus Pi times dt by 2, and then that's the thing, you were to divide by Wi, but now I'm just going to multiply by something. So now it's just going to be like times R. So R, as it turns out, is just Q mid 1, or more like NP dot linear algebra dot Q. So linear algebra dot norm and Q. Yeah, that's the thing. Or I'm just going to call it the scaling factor. So it's just R. Yeah, I'm just going to define it as R. Just this thing. So this times R. So over here, I'm just going to multiply by R and not give a shit. So basically the same time step, except So it's the same as what we were doing before, except you have a larger or smaller density depending on where you are currently. And then you have q mid magnitude as this thing. So we already did the thing. I don't think we need it anymore. So no. Then you have pi plus 1 equal to pi plus a q mid keyword arguments. That's correct so far. Times dt times. So this is the thing. You're multiplying by q mid magnitude over there. Yeah, but now we don't have to do that. We just have to multiply by r. That will do it, I guess. You could have just multiplied by, so just multiply dt by r itself, I guess. But whatever, it doesn't really matter. And then you have wi, which is wi minus np dot. So this is the thing. We don't have to do this anymore. Then, okay, so the position worlet has a half jump, then a full jump for the momentum. So this was the half jump. This was the full jump for the momentum. And then finally this thing. In fact, you don't even need this dt stuff, because r is kind of constant, so it doesn't matter. Over here, you in fact don't even need this by 2. It's just dt times r. Yeah. All right. Yeah, this is fine. Okay. And then you have q I plus 1 equal to q mid plus, so q mid, yeah, we do need that. And then q mid plus p I plus 1 times dt by 2 wi. Okay, so this is just going to be r. So far so good. This is our method. The GM values for the sun in the astronomical unit Q year, whatever. So I'm going to use this thing. Sure. Wait a second. Let me just check for any errors I might have made. No, it's fine. I mean, it's completely fine. Just compute and all. You do this whack thing, and yeah, this is fine. So now all you have to do, in fact, I'm just gonna take the full thing. Yeah, just take the whole. It's fine. And then just have the thing in method, right? So elif method equal to leapfrog. I don't know what I'm gonna call it. Adaptive step, whatever. In that case, I'll just call this thing. So this, rather than a, I'm gonna pass in gravity, just like I was doing over there. Rather than p, I'll pass in v. T is the same thing as before. Q is, instead of that, I'm gonna pass r. Yeah, I think it's fine because it's a local variable. Then lambda is lambda, so just lamb equal to lamb. Weird, but that's the way to do it. So lambda is another thing which will come to that later. It's the general relativistic correction to gravity. Come to that. Okay, delta is delta. That's our modified gravitation, right? And once again, I'm gonna wrap it in a for loop. So for I in range t dot shape 0, basically the number of rows or something like that. -1. So we're doing -1 because in the last one there's no way to update the next one because the next one doesn't have memory assigned for it. Alright, so we just do this thing, and then you also have this. So I'm not going to define this because we're not using w, and yeah, that should be the thing. Yeah, it's fine. So we'll just do that. Otherwise, unknown method. Adaptive step. No. And it's just doing the usual stuff, I think. So now I can just pass it in, right? I'm gonna run this cell. So yeah, fine. So I'm not going to be surprised if this thing fails, if this just doesn't work the first time, but let's give it a try, right? So I'm gonna go back to the case where I started the leapfrog time transform thing. Folks law like force. Hey, where am I doing leapfrog time transform? Oh, yeah, okay, I changed this thing and then it was like that. Okay, right. So you have two methods running, right? Surprisingly for Mercury with much more elliptical. Right. Okay. So I'm gonna pass in another thing, which will be so another method, which will be leapfrog adaptive step. Why is okay? I'm getting a weird lag. It's most likely because of the recording. But yeah. Let's hope this works. Yeah. Okay. Cool. Name error. Lambda. Oh my god. Did I use lambda? Oh. That's funny. Uh, okay. Gonna go there and change it. I don't like this output. It just blocks my way. That as well. Just everything's just blocking my way. Project 2, etc. Project 1. Wait, why am I at mini project 2 though? I don't know. Anyway, so go to. Okay, this is just bullshit. Why do I have these? Maybe it's just better to clear all outputs. But nah, I'll just lose a lot of progress that way. I don't want to do that. So debug. Where is the lamba? Come on. Where is it? This is plotting. This makes no sense. Yeah, better. My god, it's so laggy. So where was I? Closed orbit. And must be somewhere over there because I didn't close any code cells, right? So part 5 looks like force. Yeah, this is the one. So I'm just gonna run this. Okay, once again some sort of error. Once again a name error. So now it doesn't know what tmid is, and of course it doesn't know because I didn't use tmid. So what do? We go back to the top and we change this. So now instead of tmid it will just have t. And oh wow, why am I doing? Oh fuck, sorry. This is the way it should be because it's leapfrog time transform. And then in this one, I don't want this. I just want it. That's how it should be. Now this. Go back to the one. Yeah, I don't know why we have all of this. Just a lot of things at that point. This is just better. That's what I want. Type error. Great. What's going on? Setting an array element with a sequence. What did? Oh fuck! Why did I do t? It should just be ti. Am I stupid? Because okay, so tmid was a scalar value, but then this should be ti. Right. How many mistakes can I make today? Okay, run it again. An invalid value in square root. Is it getting some sort of overflow? Oh wow. Oh, this is messed up, isn't it? So let's reduce the steps. So I'm not gonna do 10. Okay. So I'm not gonna do this thing, just 1. And then this I'm just gonna increase. And let's see what happens. What? Out of bounds. Okay, I can't go with 1, I guess. I just can't. Okay, something weird is happening. So which one is the AS one, right? There's a red one and it's extremely closed. Oh, that's weird. guessing this isn't wait. Is 0.001 too bad a time step or something like that? It isn't going anywhere near the LFTT, which is a problem. Also, so I don't get it. Why is it having so many of these? The time transform thing shouldn't have such a problem, right? Okay, let's just actually make it even simpler. Let's just have 0 because it's going really weird. Okay. So it seems it's overlapping. That's fine. Wait, what? Where's the blue one? Oh my god, what is this? Why is it? Oh, because it's 0.001. I'm gonna decrease this. So it isn't going for a large time, unfortunately. Okay, so the leapfrog integrator just goes on, like it just keeps going. And it's also really inaccurate, I guess. I guess 0.01 was a good value. Let's make it 0.002. Oh wait, that's actually increasing. That's a bad idea. Right, just let it run. Let's see. So maybe 0.005, I guess. Let's not try that. Come on, think about it. The leapfrog time transform, it doesn't go for a lot of time. It's less than 2 years. But then this other thing is just going on and on. Why would that be? So it's like, okay, so every step it makes, it's just, oh wow, okay, I think I get the thing. Yeah, it's making those many more steps. I see. So where could we be going wrong? Hey, I'm updating DT correctly, right? Let's just see. So everything is like multiplied by r, right? Yeah. So you have ti plus 1 equal to t mid plus dt by 2 times 1 by wi plus 1, but then that's just r basically. pi times dt by 2, ti dt by 2 by w. What could be going wrong? Q mid magnitude, which is r basically, and then so I'm incrementing w. Okay, I'm changing w, and then I'm doing this thing. Sure. Come on, man, think about it. Q mid, just doing that. Okay, that's fine. So the dt thing changes, isn't it? So if r isn't working, what might work? Look, I get it. R is just a really big value, so then but then shouldn't we be able to change it by changing dt itself? It's just that it's different, isn't it? It's basically for two different times altogether. How can I change that? How can I change it to something else, right? Maybe just multiply it by another dt. That's one way to think about it, right? Or have an r maximum, and then yeah, that might be the way to do it. So in our case, the r values are actually relatively small, like 0.5 or something like that. I see. This should also pass in r max. Yeah, I'm just gonna pass in an r max. R max. This will be something which. So I'm just gonna say dt mu equal to dt times r by r max. Yeah, that's correct. And then I'm just going to multiply by dt mu instead, rather than doing all of this. So then it probably will be better, like it will have a smaller time step for that. Yeah, that's right. So r by r max, that should work. Or maybe just have r average or something like that. Or maybe, okay, so since we can't, yeah, we can't have this thing. Okay, fine. Is r max fine? It's leapfrog time transform, so I don't know. Just pass it in and see what happens. If anything, your t value will be lower, which is completely fine. I'm just gonna pass that in, right? Yeah. So whenever I do this, so whatever r in it I have, I'm just gonna pass that thing in. It's magnitude, of course. Yeah. So I'm just gonna say r init magnitude equal to np dot linear algebra dot norm, and then r init. Hey, come on, yeah. And rather than passing all this, I'm just gonna pass like r max, which is now going to be r into magnitude, because remember, we are currently at the epihelium, right? Your r is extremely positive, and yeah, I mean we do that, right? Yeah, epihelium. So for earth this is completely fine because your r is basically 1, right? But then for that other thing it may not be fine. So I'll just run this and we'll go back to the thing in question being this thing, and we'll do it for the same time step. Yeah, so this thing's r is like 0.5, so it's going to be twice, I guess, right? Let's start to run this. Once again, invalid value encountered in square root. What's going on? Okay, apparently that wasn't sufficient, so I'm just gonna go like this, I guess. Come on, run. What the hell just happened? I guess it's time transform, but man, I mean, it just blew up, didn't it? It did. Interesting. Let's try to completely ignore this. Actually, okay, I think I've changed it a bit too much. So I'm gonna go back to what it initially was, which is 10.1. This thing and these settings, right? Yeah. This is fine. So this will give us the original plot. As we expected. And then I will just take the exact same thing and I will just use a different method. No, not markdown. What am I doing? Just have a new cell, create this, and then have leapfrog additive step and not have 0.001. Also your tmax should not be this big, I guess. It should, yeah, bigger. If I figure it out. I'm just gonna pass in 2 to see what kind of plots we're gonna get. Index error. It's still going though. Why is this going? Okay, not have -3 for now. Just see what's happening, right? We'll see. So it seems R is just like increasing. Okay, not a good idea. Then maybe have some. Let's see. Still invalid value. Control is constant. How could it be an invalid value? That doesn't make sense, right? When tmax equal to 2.1 is just not working. So what you gotta do is, okay, first let's try using 0. This crazy value. See what happens. Okay, so now all of a sudden it's giving something, and the t thing is now over 50 years, but then it was just 2 over there. What happened? I'll never understand what's going on. Okay, think about it. And the trajectory is like this. It's quite circular. It didn't fix what we wanted. So there's something weird going on. The amplitude, it's just increasing. Well, this is stupid. Maybe let's make it as t max equal to 1.1 and then just have the half the time steps, so it's the same computational cost. Yeah, I hope it's the same computational cost. I don't know. And now the v thing is like this. It still has a weird sinusoidal thing going on. What is with this change? This isn't quite right, is it? No, your phi shouldn't change. Did I make some kind of mistake? Is there a bug somewhere or something? What's going on? Hey, I'm passing in the same arguments and everything, right? Yeah. The R value is changing. Sure. So I'm just gonna multiply by R, right? That should be good, I guess. R by R max. Yeah. Because R can really be lower than that. So how is it? I mean, this is just leapfrog in the end, right? It is leapfrog with an adaptive step. So how is it giving us weird stuff? Weird, unexpected stuff. T has changed. All you did was just change the time step, right? Yeah. In conclusion, it didn't work, it seems. Normal leapfrog time transform somehow works, but then this thing is just weird. Oh wow, what is going on? That's just the minimum value. I'm just gonna have some really small value and see what's gonna happen. It says invalid value in counter square. Why is that happening? A cubed. Okay, let's just see. So 107, huh? Okay, cancel this. Apparently it's this line, right? So t equal to 2 pi something. I'm just gonna copy that and then gonna find the thing. So this is where the thing is. So it's 2 by r minus p squared gm. So when it tries to do it, some weird thing. This is growing out of proportion, isn't it? Yeah. Why might that be? As if your dt has. So it is smaller than r max, that's one thing. Dt is smaller, that's all. How is that causing anything problematic? I don't quite understand. Okay. Oh, I'll think about it. Doesn't matter for what delta I do, it's just whack. Let's try doing it for a larger t value. Maybe that will change something. No, it doesn't. It doesn't. At 0.01 it's not doing anything. Okay, so let's do it like this. Let's have t being really small, so that we just have 0.1 and then have a kind of large value over here, and hopefully that will change that. Oh, okay, now we're getting kind of correct values, except so it's still a bit weird, but then it's as we would expect, which is I think a good thing. This can go one higher. We'll see. Who knows how much time it's gonna take, but let's see. So one thing I don't quite get it is, why are there these weird sort of things which are happening? It should be linear, but it isn't linear. It's doing something weird. Like I can't quite understand it. Yeah, the energy is just like that, and what the hell is going on? The orbit is correct. I won't say that that's wrong, but it is. Meaning, yeah, it is the correct thing, but it isn't as accurate as I thought it would be. It doesn't even look like leapfrog, does it? This a by m square thing is just like something weird. Even more accuracy, I guess. Yeah, probably. So it's t max equal to 0.01, and then you have dt equal to this thing. What's going on? If I'm not wrong, your t should decrease, not increase, right? Yeah. That's r upon r max epsilon. So it should ideally be the maximum. And if you look at the thing, yeah, 0.5 is the maximum. So we know for a fact that your dt value is actually effectively lower than what you have right now. So it's just gonna keep incrementing t. The maximum it can get is just the value that you have set. But that didn't happen. It somehow became this massive value, which is 6 years. Although I had only set it to be 0.1. So what happened? Why did it happen? Right? That's the question. How could this happen? I'm not using anything like squares or anything like that, right? Yeah. Is there some bug in the code? Is the update step wrong or something? It's on max. Okay, fair. So I'm just gonna assert something. So assert r is, that's just bad. What am I writing? Assert r is, so let's just use the current thing, which is fine. Yeah, so it should be less than r max, and if that doesn't happen, I'm just gonna print everything. So print I, print t sub I, print what else, the r max value, of course. Yeah, that's about right. And let's hope this gives us something insight into what's failing. Yeah, this is just something weird. It shouldn't probably happen. At least your time should be lower, right? This indicates there is some sort of a bug, most likely. Yeah, yeah, that's what I thought. It's still going though. Okay. It's not exactly less, it's more like less than or equal to it, that's fine. Just for safety, I'll also put 0.1 over there. That will be enough, I guess. Just put some really small values, so 1 e minus 3 or something. That's fine. So this should now work. Once again, assertion error. Now, so it's at I equal to 1. So, okay. The t value is 1 e minus 5, which is fine because that's what dt is. The r value is, wait, what? How did it become 0.66 something? That isn't what I thought it will be. At the very first step itself, it's just becoming larger. But it's at the ephelion, so it should become smaller. So what the fuck is going on? How is it that the r value became larger? Huh? The r value became larger. What the hell? How could that be? It's overshooting, isn't it? Most probably. I think I get it. It's overshooting, isn't it? But it can't overshoot because with leapfrog this was kind of okayish. So it doesn't make sense for it to overshoot. Your R suddenly becomes 0.6. That doesn't make any sense, does it? No. No, it does, and it's just I equal to 1. So how the hell did that even happen? Did I actually use that? I mean, I did. As otherwise, why would I have this weird assertion, right? Rmax is the correct value that we set. Okay. Could it be that DT is something weird? Just use DT. Could it be that I've just put the arguments incorrectly? I'm just gonna print it. So I don't know. Just assert. I'm just gonna print DT as well, I guess. So just to see what's going on. Over here, so assert DT, then DT new. We'll see what's going on, right? It should be some sort of really small value, but it was because it's like 1e minus 6, isn't it? Yeah, unless it's doing some weird stuff. Di plus dt. I mean that's correct. That's correct. It is. First shot is. Explanation Q made. That's right. How could it be that dt new is more than what we thought it would be? It's as if I just changed it, so how is it going above? Well, we'll see when we run the thing. So it's 1e minus 5 over there, as you can see. So this is 1e minus 5, when your dt is 1e minus 5, and this thing is 1.41. Wait, what? How the hell did it increase? Okay, because currently your R is just bigger. Makes sense, but then what? 1 e minus 5 should be enough, right, for this thing. Because in the last one I did use 1 e minus 5. It was completely fine. How is it that the r is becoming more than what it was, right? Such a small value shouldn't become more, really. There's a bug somewhere. I can't find it. So what I'll do is I'll move this upwards. Rather than asserting here, I'm just gonna move it. Now you might think, but then you don't know what dd new is, right? So I can just define dd new to be something else, I guess. Yeah. Just define it to be none, I guess. Dd new equal to none. Is that a great idea? I don't know. So I'm just gonna say dd new equal to none. Let's hope. Let's hope it works. How could it be wrong though? So now this will be the dd new before the thing. Okay, cool. Well, we know what it has to be. It has to be 1 e minus 5 because that's just the way it was. So then when I'm doing the exact same stuff as the leapfrog integrator, how is it going wrong? Oh my god. Like, think about it. Position orbit. Yeah, because pi plus 1 equal to pi plus dt, so it has to be the way. But then r suddenly became really big. Oh fuck. Okay. I get it. I get entirely what went wrong. And it was so stupid that I don't know. I want to just kill myself over it. Sometimes, yeah, sometimes it happens. Sometimes I make very weird mistakes that I shouldn't be making. But hey, let's do the thing. So now it's gonna be correct. I have a kind of a idea it's gonna be correct. So I'm just gonna reduce this. And let's see what happens now. Also gonna make 1.1 just for the sake of it. Yep. The theta thing is still a bit weird because it's in this shape. I don't know what that is, but at least it's going in the way we expect it to, like it's showing the same kind of structure, and I think that's good. Yeah, so now it's working, and we're getting till t equal to 0.8 kind of correctly. Now let me just reduce this, and then we'll get even better values. Yeah, so now you can see theta. This thing is a bit more linear. That's what we wanted, isn't it? So now going back to this setting, so we wanted the leapfrog thing to be 0.01, 0 negative 3, d max equal to 5.1. Here it's 10.1, not that it matters, so we'll use the same thing, 5.1, and we'll have both 0 and negative 3, and we'll use the same time step for leapfrog, 0.01. I think it was 0.01, right? No, 0.001, right? Am I? No, it was 0.01. Fine. So I'm just gonna run like that. 0.01, and let me just run this. Looks fine to me, at least. Oh, okay, this thing is back. Still getting some weird stuff happening, even though it's much lesser, but yeah. Hmm. Nice, let us see. I saw some weird delta somewhere, right? Ah, this thing. Think about it. Okay, okay, so remove the R max entirely. Yeah, that will be the best thing to do. So in this adaptive step, we have this thing, right? So first we delete this bullshit because it's not required. Then don't have this. So just multiply by R. No need for this assertion or anything, in fact. Yeah, remove this as well. Do the same thing over there. So no need for this assertion, delete it. Right. And call this thing. You don't have to do this thing. You just directly do that. Right, so run this. And let's see what happens. Hey, I used the QI thing, right? The correct one, I'm assuming. Yeah, yeah, that's correct. Did it. Okay, cool. So this is fine. Just run this thing. Where is it? Where is it? Is this? Yeah, it is. Hmm. Trying to see what's going on. Kind of the same, I guess. Not a lot of improvement. Let's see what happens to the. Oh yeah, so it's not changing now anymore. So that entirely changed. Okay. Now to answer the question about having or simply having an adaptive time step. Yeah. What we leave from integrator. I'm just gonna say for the leave from integrator rather than using leapfrog time transform. I present the output of, I guess, of leapfrog adaptive step. Or LFAS for short, integrated. So the same parameters, which means you have to set the T max to 10.1. So the main thing we want to look at is the theta r minimum. So that weird precision that we were observing, it's gone. As you can see, the precision that we will encounter the deviation of, that's better, theta r minimum that we will encounter for the normal leapfrog indicator isn't there. That's, I think that's correct. But you can also see slightly non-linear increase in theta, which isn't what we expect. Which isn't what physically happen. What should physically happen? Wait, is that right? It shouldn't physically happen. Wait a second, wait a second. Theta is increasing slightly non-linearly, I get that. What about in the previous one? How was theta increasing? It was also increasing. Okay, so it's practically the same thing. In fact, I can just put both of them. Whatever. So it's basically the same thing. Thus, both integrators, both methods do the same thing. So since this was like an extra thing, it doesn't have to be in a particular project. I'm just putting it there. So I'm just gonna add it in like extra this. So extra leapfrog time transform versus leapfrog step. Right. Okay, that's cool. So yeah. Effectively the same. I mean, I guess that's not correct for both methods are comparable, similar in output. That's better. Cool. Then, so this is just some other stuff. Not really interesting. I don't know what this calculation is again. I don't know. Okay. And so in this mini project 2, I'm going to add some extra. which is the rung length vector. So SO4 is a Lie algebra. I don't think anyone would understand what I'm talking about. So you guys know I kind of dabbled in group theory a bit, and one of the points where I like really sucked on was this matrix algebra stuff. So I mostly didn't understand what higher algebras are compared to just groups. I still don't understand what they are, but as it turns out, this rung length vector thing is somehow related to the Lie algebra. But anyway, so the idea is, I just want to show. Okay, this isn't the correct heading for it. Man, who cares about the heading at this point though? The first thing that we show is that the rung length vector is constant, which is once again a lot of math. And then the second thing we show is that it and the angular momentum, they form a kind of nice Lie algebra, which is called SO4. This is some high level math which I don't want to get into. Yeah, it involves a lot of weird stuff. I'm just gonna put everything there. So this is just like from extra reading that I did yesterday. Right. Rung length vector. So this is a preserved quantity, I guess, and connection with SO4. I'm just gonna read over it because I put a lot of stuff in there. Okay, so this is something which I guess I picked from statistical mechanics. There they were talking a lot about density matrices and like defining entropy based on that. But yeah, so the idea is there's this thing called Liouville's theorem, which is about how any kind of function comprising of the position and the momentum changes with respect to time in a Hamiltonian system. So, a Hamiltonian system has any Hamiltonian system has some particular derivatives, so particular ways in which your Q and P change, and yeah, so that gives us the Poisson bracket. So Poisson bracket is entirely given based on Q and P, so it's just like nabla Q F dot product with nabla P H minus the same thing but in reverse order, so stuff like that. Now this thing, like an operation on something, an operation on the other thing, minus the operation on the other thing, operation on the first thing, more like a binary operation, but whatever. This thing is called a commutator. It's widely used in Lie algebras. I mean, Lie algebras are based on this. Like, they have a thing called the Lie bracket, and for most matrix Lie algebras, that's how you define the Lie bracket. But in any case, for now, we are not really interested with how the actual group operation is and all that. In fact, Lie algebras, in fact, the Lie bracket isn't even a proper operation. It's not a group. It's going to form. Yeah. But anyway, yeah. So the idea is any Lie algebra has a Lie bracket as one operation, and the other operation is an abelian. So it forms an abelian group for the set that you're working on. It's usually noted by just the addition symbol, but it could be something complicated as well. So, for example, vector addition is one such operation. It's abelian since it's commutative. Division is basically commutative, and it forms a group. So it's an abelian group which is formed. So it turns out that a scaled version of the Raglan's vector and the angular momentum, they form a group like that. Like you add them and all that, so that will give you a sort of, so once again, I shouldn't say just the angular momentum like is a vector, but rather the components of the angular momentum thought of as a function of time. So it's very high level of abstraction, and most of it, it's pretty useless. Like I don't know why people use this stuff. Where do they use this stuff? But it's there. Okay, this exists somehow. Anyway, so yeah, we think of the functions made using the components, the entries of the angular momentum and the Raglan's vector as the elements of the group, right? So what are you allowed to do with these things? You are allowed to add, you are allowed to subtract, you are allowed to take a Lie bracket. In this case, the Lie bracket is just the Poisson bracket, right? So Poisson bracket between two such entities, and that gives you like a whole lot of different quantities which are all constants of time. That's really great, because then whatever weird thing you will come up with, if it is entirely made up of these operations, you can directly say, oh, it's a constant, it doesn't change with time, and that can be very useful, very powerful in fact. But yeah, the point stands. This is somehow related to the SO4 Lie algebra. Why is that? So every okay, why is there a KTX? Now for the other term we have, okay, I'm just gonna fix this thing. What is it saying? Hat. Oh, I've written har. Some stupid thing that I did. Oh, that I'm really doing some messed up stuff right now. Okay, so I'm just gonna search the thing. Where did I write it? Not this. Har. Sorry. Okay, better. Let's see how this is. Yeah, this is fine. Okay. So what was I saying? Right. So the first part is just that I'm like using a time evolution of any kind of scalar field. I shouldn't even call it a field, it's just a scalar function of Q and P, right? The time evolution of that as a function of the Poisson, I mean, as given by the Poisson bracket, and basically proving that the Poisson bracket of A vector, which is the Raglan's vector with H, is 0, which is a lot of complicated math, but it turns out to be 0, right? And thus we say that the derivative of this Raglan's vector itself is 0. Of course, what we really mean is that the derivative of each component is 0, because when we say Poisson bracket of a vector with H, we just mean the Poisson bracket of each component with H put in a vector. So we already know that angular momentum is also a conserved quantity. So what this all of this means is that any function that you would create using components of A and L is also conserved. In fact, it's not just functions which are like, so here when I say functions, I mean just normal addition, multiplication, exponentiation, these kind of things which are just same functions, right? But then you can also have some messed up things, which is basically like taking another Poisson bracket on two of these quantities, for example. So due to the antisymmetry property of Poisson bracket, we have this thing. So this is like, the first line is pretty obvious, just the derivative of Poisson bracket AB is just the Poisson bracketed with H again. But then we use the antisymmetry property of the Poisson bracket and we get this thing. So it's the Poisson bracket of A with the Poisson bracket of B and H, the Poisson bracket of B with the Poisson bracket of A and H. Now for any kind of like components, right? So Li, Aj, where Ij are like which dimension are we dealing with? Yeah, so it turns out, because the thing is, like, any of these components, if you put them as, let's say, A or B, right? So B with H, right, that Poisson bracket is 0 because it's the derivative is 0, right? Yeah, and we already proved the Poisson bracket is 0. Similarly, AH, that thing is 0. So then A with 0, that Poisson bracket is also going to be 0 because 0 is a constant. So any kind of partial derivative of that is also 0. So this whole thing turns out to be 0. What that means is any kind of Poisson bracket is also constant. Of course, when I say any kind, I just mean Poisson bracket between the components. And this, I think, is more than enough for us to define what we want to define. That is, we are defining the Lie bracket, so the Poisson bracket as the Lie bracket for a Lie algebra, right? This is what leads to the SO4 group because you have this nice property. So like everything that can be constructed using this is what we are after, and it turns out that SO4 can be constructed using this, right? As uses, so okay, so we're just right now just comparing the commutator table for the D vector and L vector, and then we are also going to compare the table for these antisymmetric matrices that we have for the actual SO4 group. So SO4 Lie algebra, this should be Lie algebra over there. Okay, so this shouldn't be the SO4 group, it should just be the algebra. Now, more like now for the antisymmetric 4, not even, yeah. Now, for the antisymmetric 4x4 rotation matrices that rotate in the I-shaped plane, we can define the commutator AB as AB minus BA as the group. Okay, this is once again not what we want to do. Just have this thing. Then this gives us the next commutator table. So this was similarly a commutator table over here. So you can see this thing is 0. This thing is supposed to be negative over there, but then that's not negative. That's fine. Not a big deal. Yeah. So you'll see it's exactly flipped. That's all, right? Seems like it. Okay, so some off diagonal entries are also 0, aren't they? Yeah. The 1, 2 isn't there. Okay, cool. Let's not negative D3. Interesting. So how many are there between the dimensions? We know we have 3 dimensions. So it's just, oh wait, actually 4 dimensions because it's SO4. So it's 4 choose 2, which is 6. Over here as well, we have 6 components to deal with. Right. So I guess we have to first arrange this in the correct way so that it's going to work out. So I don't know if isomorphic is the correct for Lie algebras. So I'm just going to put all of this into Gemini and have it correct the table. Charging, don't I? I'll be back in a moment. So in the context of Kepler orbits and Raglan's vector, we have this. Okay, how to show, how to map components of vector L and vector D to the antisymmetric matrices, so that the commutative tables are alike. Unit plus Jij, where the indices are in I 1 2 3. Okay, so L1 gets J23, L2 gets J31. So you're using the cyclic notation. And L3 is J12, and the same thing with D1. It is under commuter table. Okay, can you rearrange the commutator table for Jij so that it looks exactly like the table for vector D and vector L. Note that to perfectly match the signs, you use the identity J31 equal to J1. Export to sheets. No, I don't want this. Give me markdown. Give me markdown code for this table now. No, don't put the L and D components in the code. I mean, this is nice though. Okay, so now I'm just gonna replace this whole thing by that. Actually, just put it over here to see what's the thing. And yeah, weird how that works. Okay, so now I guess it's the exact thing. Yeah, so I'm just going to edit it and delete all of this. That's at that point it's clear that there is an isomorphism. So then D1 corresponds to J14, D2 corresponds to J24, and D3 corresponds to J34, whereas L1, L2, L3 correspond to these J23, J13, J12. Right. And now it's exactly the same. Yeah, looks correct, doesn't it? So, okay, I think this is enough of exploration, I guess. Just to see, okay, Lie algebra definition. So it's a vector space over a field F. So any vector space is basically just like a sort of abelian group. Yeah. Equipped with a non-associative binary operation called a Lie bracket, which puts it from G to G to G. This operation must be bilinear, satisfies Q symmetry. So our case does that, right? And satisfy the Jacobi identity, which is once again a kind of commutator does that. That's pretty much it. That's all you need to define a Lie algebra. Now, how is it related to the SO4 group is the I think the main question, right? Yeah. So the capital SO4 group is over multiplication, which is very different from this thing. So how do we come up with a way to do it? For the SO4 Lie algebra, is there a way to define the matrix multiplication operation? Using Poisson brackets, using the Lie bracket and the addition operation, addition slash subtraction. This is the same thing. I mean, a subtraction is basically just addition with an inverse. What happened to this? Okay, I hope there is. No, if you're looking at the Lie algebra, so full in isolation. The universal enveloping algebra is a specific property of the SO4 n generators. Oh, okay, cool. That's the symmetric part. Okay, so this is just a lot of weird stuff. The Lie algebra or a Jordan Lie algebra structure. When you find a product, if you embed the algebra into a larger structure like the 4x4 matrix space or the Clifford algebra. Okay. Oh wait, I don't want this. What the hell is this thing? I don't want that at all. It's not a simple algebra, it splits into two. Wait, so capital SO4 is a group. It's a special orthogonal group. It's not the Lie algebra. What the hell is going on with this? Oh my god. Okay, but here's one thing though. So you can write. So for you know this particular algebra, you do have this thing, and that can be really useful, I guess. Just the symmetric part. What the hell is the symmetric part? The identity for the product that you gave. Does it then dimensions to the DNL component. Involving delta ij. Involves the export dimension by path of the component. So we're saying d1 square is negative 1, which means that's a very weird thing, isn't it? This thing is negative 1. Wow. You know that the commutator is there, but then this product. What do the actual. Huh. Report algebra, will the generator satisfy this? Okay, what's going on? At this point I'm just getting really confused. D1 D2 and then how this is half L3. What about L1 L2? Okay, just thinking about it. L1 L2 equal to negative L3. Interesting. Very interesting. How would that be? And the angular momentum stuff is just very messed up, isn't it? But I mean, think about it. You first take the nabla with Q, and then you take the nabla. So, what is L? L is just R cross P, right? Or Q cross P if you want. So you first take nabla with Q. What does that give you? Nabla with Q of this big thing. And then you go that. Okay, interesting. Nabla with Q. That's the identity matrix over there, isn't it? Yes, it is. Sure is. So the cross product is just the antisymmetric matrix. You can think of it like that. Oh my god, this is some messed up stuff. Okay. But then since it's just the dot product with the nabla with P, so I guess we can just do it element by element, right? Yeah. So we can just do like with Q1, then with P1, and then just multiply these together. So if I just take the nabla with Q1, it's basically the 1000 cross L, so cross P vector thing, and then plus, so since I've taken the nabla with P1, so the relative P1, then it's just like the Q vector crossed with 1000, right? So effectively it's just the 100 vector crossed with Q vector minus P vector, which is messed up because that doesn't have any kind of dimensions. What? Wait, what? Dot product. Oh, okay, no, you don't add, you multiply it, sorry. So you just take a dot product of these two, right? Yeah. Man, this is some messed up stuff going on over there. Okay, come on, think about it. Okay, so I took a dot product of these two. I can sense something bad is going to happen if I do that, but think 1000, right? That crossed with this. So it's basically like rotating one by 90 degree and the other by negative 90 degree and then just taking dot product. Yeah, that's effectively what we did. Very weird. But that's 100 crossed with this, right? The only components that you will have are the first two. The third is gonna die out. Yeah, this is messed up. This is just fucking messed up. Okay, I'm just gonna ask it. Can I define the multiplication to be nabla sub q a b equal to nabla sub q a nabla sub b b? Is a portion of the Poisson bracket definition, right? However, defining your multiplication would not be consistent with the algebra matrix. Okay. No. Okay, this isn't understanding. No. Still define the Poisson bracket as the Lie bracket but define the multiplication that we discussed how was it giving us I'm just gonna copy this thing. Hopefully I can copy it. Let's see. There's the portion. Mapped back to a specific operation in the physical plane. Okay, Lijj. Okay, these are scalars. When you multiply two functions in the classical mechanics, you just get another function. It's a commutative operation. However, the 4 cross commutator is that's fine. Okay, this is I think something. Advanced math, yeah, that's probably gonna think again. I don't think so. It understood it as just normal multiplication, which is stupid. product, which is just this thing, right? The 4D angular momentum generators as J mu t equal to, huh? Okay, so instead of Q and P, they're just using this weird, these weird symbols. That's all. So now they have the 4D angular momentum generators. What the? Okay. So now they're thinking, oh, this is like a four-dimensional space. I don't quite get what's going on, but it's fine. Yeah, sure. One-sided Poisson bracket in the 4D space. Okay, so this is just a Lie bracket equal to. Is this the Lie bracket? Oh, it is, because yeah, it is. This is the same identity that it gave us, then plus a symmetric term. So the Lie bracket is the anti-symmetric part of this derivative operation. Okay. The symmetric part of the derivative operation, which is scale constants. Okay, this is some weird math. I think nobody has exploded, and that's why it can't answer it. So if nobody has exploded, it probably doesn't exist. This is just enough. So it has no direct connections with capital SO4 in that sense, because with capital SO4 there is a sense of a group operation. The group operation is multiplication, but here we don't have that. So this is how we do it, right? Yeah. The Lie algebra SO4 is very different from the capital SO4 thing. That's a vector space. This thing is a different thing altogether, right? Because capital SO4 is a special orthogonal groups. This thing is just stuff made of the anti-symmetric matrices. So different, I guess. Isn't that the case? SO4. What the fuck did I just write? SO4 group definition. Four cross four real orthogonal matrices with determinant of +1. That's the thing. An anti-symmetric matrix, which is a 4 cross 4 matrix, well, that also has a determinant. Yeah, sure. But then that's the thing, right? It's an anti-symmetric matrix, so it actually has a determinant of 0, isn't it? All orientation preserving rotations. Yeah, that's about right. The Lie algebra has 6 generators, which can be interpreted as 3 rotations in x, y. Okay, fine, whatever. So SO4 group versus SO4 Lie algebra. So that's the thing, it's a skew symmetric matrix. Now, skew symmetric matrices, yeah, that these have these things, and then by definition the determinant is then 0. So this has no relation whatsoever. This is the thing. This is the problem. Like a special orthogonal 4 uh, the SO4 Lie algebra is just so different from the SO4 group, right? Right. Because here you have determinant 1, there you have determinant of 0. This makes no sense, does it? Wait a second, what? No. Wait. If you have A transpose equal to, so we know that the A transpose thing is just that way. Wait, isn't every skew symmetric matrix having a determinant of -1? I am confused. Because -1/4 is 1, isn't it? So then this shouldn't matter. The determinant of -A, if A is a 4 cross 4 matrix, would just be A. What happens with 2, for example? The 2 cross 2 matrix just has determinant like that. But if I make it negative, it's still just the same thing, right? So the determinant actually stays the same. So I can't say it's 0. No, I can't. For odd numbers, it is 0 probably. Is the determinant of a skew symmetric matrix 0? I mean, I know this is like just a very basic question, but then I don't think it is. Like, not from what I've learned. R 4 cross 4. Do 4 cross 4. Skew symmetric matrices. Zero determinant. I don't think so. No, they don't. Odd order always has. That's what I thought. Yeah. So no, I can't say it's determinant 0. So then probably these are also. So they are representing rotations, right? And then the determinant is also 1. No, they are also part of the capital SO4 group. But then that doesn't mean that it's. Yeah. Very different than what I thought. And it's also not like that any skew symmetric matrix is going to have a determinant of 1, because you can just scale it up and then still skew symmetric. So what does that mean? If you're also defining addition, then the Lie algebra obviously consists of things which are, well, not in the SO4 group. Right. Obviously, like, even capital SO4 group itself has things which are not skew symmetric, but then we know that since if you just have the access to the Lie algebra operations, the Lie bracket and the addition, we're only going to get skew symmetric stuff. So yeah, that's just a messed up thing, isn't it? So everything will be made of some addition of these skew symmetric matrices. So you're stuck in that plane in a sense, and then the SO4 is like a sphere, if that's, yeah, that's one way to think about it, that the intersection is, it's not like one is a subset of other, both are different apparently. It's the 6-dimensional vector space. So yeah, as it turns out, this isn't directly related to capital SO4, although these do represent rotation matrices in a sense. Some sort of rotation, I don't quite get it, but yeah. Okay, anyway, enough of group theory. I think this is enough. This is enough exploration to get many kind of bonus points that he would want to give. But yeah, probably it. Okay, so that does it for the second mini project. Now I'm just gonna do the third mini project real fast. Before that, just let me push this thing. Extra. submit it by the end of today, I guess. And that's one. Now we want to go to the other thing, so I'm just going to pull up this and we'll do it. We should probably split it, right? Split the thing. We don't want this here. Okay, cool. So that's planetary motion. Relation of conventional with SO4, that's done. The next thing that we want to do is obviously, so Kepler orbit is done, right? One closed orbit is done. So movement is done. The Young length vector is done. The leapfrog time transform thing is done, and it's stupid. We figured out it's stupid because we can do much simpler method than that and still get the correct results. Solution of differential precision. It was relativistic. We did this. We have done this. No big deal. Star wobbles, and yeah, this is where we want to go. So star wobbles and exoplanets. So I'll do this, but before that I'll take a break. See you guys in the next video.